Hello, my name is Branko Nečemer and I am a young researcher at the Faculty of Mechanical Engineering in Maribor, Slovenia. Today I will present our research work with title Fatigue Crack Growth in the re-entrant auxetic structure. In the scope of this presentation, I will first introduce the cellular porous materials and auxetic cellular structures. Then I will present the selected material and specimen geometry. After this, I will present the experimental investigation, which includes static and low cycle fatigue testing. I will also present a computational model for fatigue life prediction of auxetic structures, and at the end, I will give conclusions. First, I will introduce the cellular porous materials. The cellular porous materials are a relatively new class of metamaterials. In general, the cellular materials can be divided in three main types: honeycomb structures, open cell structures, and closed cell structures. Cellular porous materials have a good combination of mechanical and physical properties like mechanical energy absorption, sound isolation and damping, floatability, durability at dynamic load, and recycling. The most important material parameter of the cellular materials is the relative density, which is given by the equation below. A recent type of cellular metal is the auxetic cellular structures, which exhibit a negative Poisson ratio, which is causes in different mechanical behavior. A material under compression becomes thinner in cross-section and vice versa in tension. The auxetic structure have better physical properties compared with conventional cellular materials like stiffness, fracture toughness, energy absorption, damping, and so on. The auxetic structures are useful in various applications: aerospace engineering, automobile industry, and mechanical domain. At the bottom of this slide, you can see different geometric types of auxetic structures. The case study is the experimental and computational investigation of the fatigue life of the re-entrant auxetic structures. In this study, we analyzed two geometric layouts of the base cell, so the re-entrant and rotated re-entrant structure. The difference between these two structures is in the rotation of the base unit cell. Material and geometry of the specimen. In this study, the compact tensile specimen with two different orientation of the unit cells were used. The figure below presents the dimension of the specimens. The specimens were fabricated by using abrasive water jet cutting technology from a 3 mm thick sheets made of aluminum alloy 7075 T651. Experimental test unit. All experiments were performed at testing machine Smithsweld. For specimens attachment, we specially designed the clamping jaws which prevent the lateral deflection of the specimen. In the scope of the experimental testing, we first performed three static tests for each structure to determine the static curve. After static tests, we performed low cycle fatigue tests. The fatigue tests were performed in a load control at load ratio 0.1 in tension. We select 5 loading levels and performed at least 2 tests at each loading level. Experimental results of the static tests. In this slide, the static curve for the re-entrant and rotated re-entrant auxetic structure are presented. Based on static curves, we determine the loading level for the low cycle fatigue test of analyzed auxetic structures. At the bottom of this slide, the fracture path of analyzed structures under static loading is presented. Experimental results of low cycle fatigue tests. In this slide, the experimental results of the low cycle fatigue test are presented. In the experimental test, the 5 loading levels were selected. The total fatigue life of analyzed auxetic structure was determined after the failure of the third cell connection. The experimental results are summarized in the diagram below. From the diagram, it is seen that the fatigue life curve of the re-entrant and the rotated re-entrant structure are very close. At the right side of this slide, the fatigue fracture path of analyzed structure under dynamic loading is presented. Based on the obtained results, we can conclude that the unit cell's orientation does not influence on the fatigue life of the analyzed auxetic structures, but only affect on the direction of the cell fatigue failure path. Computational modeling. In the presented work, the computational model was built in the ANSYS software package. The boundary conditions were prescribed in the reference points A and B, which are in the center of the clamping holes. In the computational analysis, the external force was defined as one closed sinusoidal loading cycle between the minimum and maximum force, like shown in the figure below. The external force was prescribed in the reference point B. The geometry was discretized by using two-dimensional plane stress linear finite elements, where the average global size of the finite element was set to 0.3 mm. In the computational analysis for the material model, a multilinear plastic kinematic model was applied. In computational model, the elastic part is modeled by defining Young modulus and Poisson ratio, while the plastic part is modeled by defining plastic data pairs obtained from the cyclic stress strain curve, which is given by these two material parameters. For the fatigue life calculation, the strain life approach based on Coffin-Manson model with a more mean stress correction was applied. In the framework of the ANSYS program, the strain life parameters were integrated into the material model. The strain life parameters include all four Coffin-Manson equation parameters. The Coffin-Manson's material parameters are presented in table below. Fatigue calculation. The fatigue life of analyzed auxetic structure is determined using strain life approach and with consideration of more or mean stress correction. The total fatigue life of analyzed specimen represents the sum of number of cycles to failure for the first three cells. So this means that we first calculate the number of cycles to failure for the first cell. In first step we calculate the period N1. In the second step, we cut the first cell strat and repeat the computational analysis where we calculate the number of cycles to failure for the second cell, period 2. In the third step, we cut the second cell strat and repeat the computational analysis where we calculate the number of cycles to failure for the third cell, period N3. In the end, the total fatigue life of analyzed structure represents the sum of all three periods. Results comparison. In this slide, the computational and experimental results were compared. From the diagram is evident a good correlation between the computational calculated and experimental measured fatigue life curve of the re-entrant and rotated re-entrant auxetic structures. The comparison between the computational and experimental results has shown that the measured fatigue life and observed crack path are very similar for both structures. Based on this similarity, it can be concluded that the proposed computational model is suitable for the simulation of the fatigue behavior of auxetic cellular structures. Conclusions. In the scope of this research work, the fatigue strength investigation in dynamic loaded re-entrant and rotated re-entrant auxetic structure was performed. The experimental results showed that the fatigue life of analyzed structure are almost the same, while the crack path was not. Based on this, we can conclude that the unit cell's orientation does not influence on the fatigue life of the analyzed auxetic structures, but only affect on the direction of the cell fatigue failure path. In the computational approach, the total fatigue life of the analyzed structure represents the sum of number of cycles to failure for the first three cells. For each of the three cells, the number of cycles to failure was calculated separately. For the next cell, the seam between neighboring cells is considered during the further computational analysis. The comparison between computational and experimental results has shown that the measured fatigue life and observed crack path are very similar for both structures. Based on this similarity, it can be concluded that the proposed computational model is suitable for simulation of the fatigue behavior of the auxetic cellular structures. Thank you for your attention.